Hello and welcome. So today we will start our module number 9, which happens to be tissue engineering with light. And in this module, we are going to discuss the direct application of laser light onto human tissues. Previously, we have discussed photodynamic therapy, where either a specific type of chromophore, specific type of a drug, or something else like photothermal therapy. You have seen gold nanoparticles. They have been used, which interacted with laser and thereby created either reactive oxygen species or generated heat. Here, instead of any of those intermediary things, we are going to apply directly laser light onto human tissue for the purpose of tissue engineering. Now, all of or at least some of you engineers, not the biomedical engineers of course, but maybe perhaps the electrical and electronics engineers as well as the physics people are wondering what is tissue engineering. So, here is a useful chart for you. Tissue engineering, it's a discipline of the biomedical engineering, and it uses various methodologies. It uses cells, different types of materials as well as engineering concepts to restore, maintain, improve or replace different types of biological tissues. Replacing or removing or restoring, maintaining of biological tissues are of one of the primary importance for the well-being of a person, right? Certain valves gets damaged, or you have known about angioplasty or retinal detachment or some wound healing or skin grafting. All of those things can be faithfully, reproducibly, safely done by the process of tissue engineering. Tissue engineering is a very strongly coming up subject, is a part of biomedical engineering, and I hope to see, like you these days in engineering colleges see disciplines such as civil engineering, mechanical engineering, electronics engineering. I hope to see tissue engineering in itself coming out of biomedical engineering as a discipline rather than a chapter or rather than a subject or rather than just a small additional topic that biomedical engineers needs to study, because tissue engineering has the capacity to, believe it or not, convert human beings into superhuman beings. So, what does tissue engineering actually do? So, I discussed a bit about stem cell therapy. It utilizes either stem cells or some kind of a culture, some kind of a growth factor, some kind of a scaffolding, etc. Insert them into human body to, as I said, to either replace or maintain or improve the quality of life, improve the health condition of the person. So, again, as I said, tissue engineering needs to come out and create its own discipline by itself. I am taking this opportunity to teach you a very common and a very interesting topic of tissue engineering, which is not directly related to biophotonics per se, but by giving this example, for those of you who do not know or are hearing tissue engineering for the first time, will come to a clear understanding what it is. So, we are creating artificial human hair, human ear, beg your pardon, artificial human ear. So, this is a lab made ear, right? And no, this is not made up of plastic, this is made up of the same material, which is cartilage, which our ears are made up of. We can create in a petri dish, this is a petri dish, you all know, and putting it under certain sets of condition, temperature, pressure, pH, and by adding some cartilage cells, it could be stem cells or certain similar things with proper growth conditions, proper factors, biomedical students know this. Under certain circumstances, you can actually grow them. Nowadays, there is 3D bioprinting. Must have heard of 3D printing. it is coming up very strongly. 3D printing is coming to be used in tissue engineering. We are able to generate tissues in a petri dish. We are able to generate tissues of specific shape, size, color and texture in a petri dish using either stem cells, that is easier thing, or normal cells. We reprogram it back, or just any cell taken from any other part of the body, converting it into. And there is a very nice example of utilizing these kinds of tissue engineering to regrow. Yes, you have heard the term regrow a human ear. So, I ask you, this is my reference here, I ask you to go through this paper and read through the fascinating, surgical as well as the medical procedures these doctors were able to do. So, this child was born with this congenital ear defect where the ear was not formed. You must have seen these kinds of disability or defects. Defect is a bad word in this case. Disabilities coming up. This is a congenital problem. And they have regrown a ear made up of cartilage. It's not made up of plastic or any artificial material. It's not those artificial limb or artificial leg that sometimes people who have either gone through the process of amputation or some kind of accident add. This is not artificial per se in that regard. This is not made up of plastic or metal or wood or any such thing. This is actually cartilage. The cartilage is the softer tissue that covers the bone or that forms part of our ear and some part of our eye and several portions of our body. These are not as hard as bone, at the same time not as flexible as muscle or skin. They are somewhere in between. You know what cartilages are. So, they created it with a cartilage, put it surgically, put it inside the child's ear and giving sufficient growth factor, the body actually accepted the ear of as its own, meaning as the child will grow, the size, shape, characteristics of the ear will grow as well. In artificial limb or those kinds of thing, crutches or similar thing, they are fixed. They are made up of plastic or metal or wood and they do not grow. Jaipur foot, for example, fantastic as it is not the real thing. Here the body has accepted it, and after few years, few months, as you can see that the body will start growing blood vessels onto it. So that after certain time, if this ear, this so-called artificial ear that has been implanted on the person's body get injured, it will bleed. It will bleed. So, this is what tissue engineering is. This is what tissue engineering is. Now, obviously, you will understand that cartilage, one type of tissue, and it is somewhat easier to make, though easier in relative terms, but this is just a start. This is merely the beginning. Think of the possibilities that we could do. We could replace a limb, we could replace maybe even torso, any other part which has been injured or which has been lost due to some sort of accident or birth defect. Can be replaced. Tissue engineering is showing this potential. Tissue engineering is showing this potential that a lost body part can be regrown in a lab and then surgically inserted into the person, and it could be an external limb, external organ, external appendage, or it could be an organ. Why not? If we can grow ears, can we not grow kidney? Instead of waiting for some kind of a transplant, let us grow a kidney into the laboratory made up of the stem cell or made up of the cells that the person herself or himself possess, create something like this and insert it into the person's body. There will be complete acceptance that needs to be accepted, the complete acceptance, or the chances of acceptance from the person's body is much more to a lab grown, stem cell grown kidney rather than something transplanted from another person. I know I am simplifying it tremendously, and medical students are scoffing that there is a huge amount to unpack, and obviously that's what I'm saying. Tissue engineering needs to be a discipline like civil engineering, and I under no circumstances am trying to pretend that I can explain it to you within 2 or 3 minutes, but I am abreasting you to the possibilities that tissue engineering produces, and this is not necessarily directly related to biophotonics, but I want you to know this because this is fascinating. So, where is biophotonics coming up in this? That is what we are going to discuss. We are going to discuss laser induced tissue engineering or laser based tissue engineering. That is the course module number 9. That is what we are going to discuss, and it is this module is quite not that intense. I know several of my modules have been 1 hour instead of 30 minutes. I will try to finish them. These are mostly examples because overall, I assume the overall theory whatsoever beforehand. So, I think my work will be easy. So, laser based tissue engineering mostly fall into 3 categories. First is the tissue contouring and restructuring. Here tissues are mostly used to ablate, basically make some kind of incision, make some kind of it's a destructive process overall. It's basically localized heating and then a removal. Ablation simply means destruction or cutting. It changes the shape or changes the pigmentation of the tissue. This is the coloration of the tissue. Then there is tissue welding. It's just like metal welding. 2 metal plates are joined together, and you have a welder with a high power heat source or a laser source whatsoever converts the junction between the 2 plates into molten state, and these molten 2 metals, the junction fuses, and upon cooling they become one single plate. So, tissue welding is very similar thing. Welding or soldering to fuse tissue, and this is used in some kind of a wound healing or repair a tear, some kind of blood vessels have ruptured, or in your retina has got detached, something similar, something that has broken, needs to be fused, needs to be connected. And then this is slightly controversial, and we are going to take it head on as well. Tissue generation, where supposedly underlining the mark, supposedly laser activation stimulates new tissue generation. So, by sending laser light, you are creating the tissue to grow, or the tissue or the cells to proliferate, and thereby form it's a growth. So, it's just the opposite process of restructuring. You are purposefully damaging the tissue. Here you are regrowing the tissue, and this is coming up very strongly, but the jury is still out. We are still not sure about the science. So, whatever we are going to discuss, I have dedicated almost a separate chapter for this, and we are going to discuss this at detail. But overall, laser based tissue engineering more or less falls onto these 3 categories. So, where exactly do you want to use them? Like, for example, laser ablation or reconstruction. So, I will pretend to pronounce it like I know. Otolaryngology. Medical students come to my help. This is, well, carbon dioxide laser is used to create intense localized heating, and basically it produces necrosis. You burn the tissue out, tumor or something like that. Dentistry, ablation of both soft and hard tissues and excising materials from both mucosa and gingiva in the oral cavity. What does gingiva? I just learned this new term. What does gingiva means? I know dental students are giggling. It means gums, gums where your teeth are connected. Mucosa is the upper line. So in dentistry, you are going to destroy some part of the soft and hard tissue for oral or mucosal surgery. If you have some sort of a tumor, some sort of incision, some sort of a wound, something needs to be done. This is basically burning of a soft tissue, something that has damaged, maybe cancer. And angioplasty, I discussed about angioplasty beforehand. Here, the laser based angioplasty, instead of PDT, you are directly putting the laser and destroying the plaque, here. This is the balloon tipped catheter. I discussed about the balloon tipped. The balloon opens up the artery, and see how it has gone. You insert your catheter, which could be an optical fiber tube, and it goes inside the heart, and then it goes through the ventricles or the smaller capillaries, which when I zoomed, you can see that the balloon tipped catheter or balloon tipped angioplasty had happened. Right, this is, so how small, this is the zoomed in version. So how small this area might be, what would be the diameter? Is this thinner than the width of your hair? What do you think? This capillary inside your blood, inside your heart, do you think this is thicker or thinner than a strand of your hair? I also asked what happens when the balloon is removed. It might fall back. So we usually put a mesh, some sort of a strong and sturdy material permanently being put, involving placement of a mesh. Mesh is basically a net which supposedly does not, it basically keeps, it's like a scaffold thing, it keeps the artery open and doesn't let it collapse. It's made up of either steel or any other kind of implantable material, and the idea of this mesh is it should not be interfering with either the blood flow per se. Well, obviously it will open up, but it will not have any adverse allergic reaction to the body. So that's the idea. We put a permanent mesh. So laser destroys these plaques or heats it up, melts it down, and the balloon opens it up, and then you put some kind of a mesh behind. So these are all tremendous surgical procedures that could be either done directly or with the help of laser. So what basically laser does, laser burn or produce localized heating at a specific area without damaging the surrounding places. That's the overall idea. Here, however, unlike PDT, since it is a direct laser connecting with the tissue, you have to bring the laser light pretty close to the area, of your operation. That's the requirement. So usually it has found application in either dentistry. I have a dedicated lecture for laser based tissue engineering in dentistry, or in dermatology, skin basically, where you can directly bring, or in ophthalmology, eye. So these are the three major areas. However, the other areas are there. Today in this module I am just giving you the introduction. So tissue welding, on the other hand, it utilizes the energy of the laser beam to join or bond tissues. As I said, what does welding actually means? The absorbed laser energy can produce alteration in the molecular structure of the tissue to induce bonding between neighboring tissue structures. The same thing, two metal plates, by heat you are fusing them together. They are liquefying, but the liquefaction is with the help of a laser is only at the periphery or at the junction or at a specific area, which is helping them, which is basically altering their molecular structure. Previously they were solid, now they have they got more energy, they are liquefied, so the molecular structure has changed, and this molecular structure is used to fuse two different types of tissues, and then upon cooling they combined together. So, and this is a non-mechanical and non-contact. So, where suturing or stapling is difficult. Suturing is basically stitching. You know, when you have wound or some kind of a deep wound, doctors stitch that area. Many of you might have got stitches as child. I surely got several because I used to run quite a lot and fall down more than that. So, suturing in my knees and places where the stitches are done. So, where it is difficult to suture, say for an internal injury or even stapling, perhaps you know we do stapling as well for a proper procedure for wound healing. Now, tissue welding is being used more and more, and it is non-mechanical and non-contact. I won't say it is painless, though some people claim it. It's definitely not painless. Trust me in this one. But it's suitable for cases where these are difficult. If it is a normal surface wound, doctors are still doing suturing, stitching, but tissue welding is coming up. This is very strongly coming up in wound healing. So, basically you use short pulse lasers to limit energy output, right. You do not want to melt the entire area, you want to melt specific tissue, specific cells, and then they need to get coagulated and fused together. If you have completely killed off the cell, if you have completely caused necrosis, remember from last class what does necrosis actually means. If you have carbonated the cell or carbonated the tissue, charred the tissue, then obviously it is not going to work. You have to make it with a specific power with limited energy, and obviously you have to select the laser wavelength that is only absorbed by the targeted cells. Say for example, you are targeting epidermis or dermis part of your skin. So, you have to ensure that that needs to be selective and specific, and then you can add some kind of a chromophore beforehand to increase the bonding strength, but that comes at a later stage. That is important, but not so important. These two things are important. So, basically you are generating heat directly onto the tissue by laser light. Laser is getting absorbed, certain photons of the lasers are getting absorbed by certain organelles, certain cellular components, certain part of the tissue, and upon absorption of heat, either they emit heat or emit light, or they basically dissipate heat. Their molecular structure change, and this molecular structure change and their dissipation of heat is being utilized to engineer, to mold, to restore something that has gone bad. Very simply put. So, as I said, this is going to be a very small and very easy chapter. Mostly examples, I will show you pictures and that's it. So, these are again the most of the topics that I discussed: tissue engineering and laser tissue engineering. Biomedical students, or those of you who are non-biomedical but have strong interest in this regard, I strongly suggest you to look into tissue engineering very seriously. This is a fascinating topic, and though it does not directly come under the realm of bioengineering, it is coming up very strongly as something of a middle ground between engineering and medicine directly. So, this is the paper that actually discuss how the ear was grown and then it was fused into the patient's and this is patient specific ear shape. So, it is not just a random ear of any XYZ shape that you have grown into the lab and fixed to the child. It has to be of a specific shape, and it's a very interesting paper. Please go through it, and I'll see you in the next class. Thank you very much.